this lesson, we're going to be stepping away from the normalcy of trigonometry, where we're solving for angles and solving for sides and triangles, and looking at a different topic surrounding trigonometry called trig identities. In trigonometry, an identity is some relationship that's between trig ratios that is always true for any given angle. We're going to be asked to prove that certain identities are true. In order to do that, we're going to use two basic identities as well as three reciprocal identities and use those as tools to help us prove that an identity is indeed true. To start, we're going to need to figure out what these two basic identities are. The first one is called the Pythagorean identity, and it goes like this. The sine of any angle squared plus the cosine of any angle squared will always equal to 1. Now I'm going to prove this in just a second, but one quick note on the notation of how we write sine theta all squared. You'll see here that this squared is actually right beside the sine. Now, what this means is that this sine function, theta, is all squared, but instead of writing it like this in brackets, we sort of shorthand put the squared beside the word sine. This doesn't mean that we're taking this word sine and squaring it, because that wouldn't make any sense. These things are equal. Sine theta all squared, we shorthand to just say sine squared theta. It means the same thing. Just like cos squared theta is the same thing as just taking cos theta, whatever that happens to be, and squaring it. Okay, so let's prove how sine squared of any angle theta plus cos squared of any angle theta always equals to 1. To do that, I'm going to use this diagram right here, and I'm going to draw a terminal arm coming off just like that. And inside of this terminal arm, I'm going to put a theta. Now, a lot of times we've used cast rule or other means in order to interpret what this theta will be. And to help us out, I'm going to draw our right angle down to the x-axis here. So I'm just going to draw a line up through there. And this creates a right angle. And I'll say that it meets at this point P. Now this point P, we don't know the coordinates, we're not defined, but I'm going to call the coordinates x, y. And here's what we know about this right angle triangle that I've drawn. If this point P has an x value of x, that means the distance from the origin all the way over to where that point lies on the x-axis has to be a distance of x. Same goes with the distance from the x-axis up to the point. That has to go up y units. Now, we can define this hypotenuse as something as well, and we're going to call this r. To prove that this Pythagorean identity is true, what we're going to do is substitute in sine values for theta, cos ratios for theta, and see if we can end up always equaling 1. Well, we know through SOHCAHTOA that the sine of any angle is equal to opposite over hypotenuse. In our case, the diagram's opposite side from theta is y, and the hypotenuse side is r. So we could say that this is going to equal y over r all squared. We also know that cos theta, for using SOHCAHTOA, is adjacent over hypotenuse. The adjacent side to theta is x, the hypotenuse is r. So we can write this as x over r all squared. Of course, right now I'm just focusing on this section of the identity right here. So I'm just going to put an equal sign just for this section. Okay, well let's Now, simplify these things by squaring all of them. So y over r all squared is just y squared over r squared. And x over r all squared is x squared over r squared. And when we combine these things, well, we can see that they already have common denominators. So I'm just going to rearrange this and say x squared plus y squared, those are the numerators when we add them together, over r squared. Well, one other thing that we know about right angle triangles is they have the Pythagorean theorem. And the Pythagorean theorem states that x squared plus y squared equals r squared. Well, look at our equation here. We have an x squared plus y squared, and if we're saying that that's going to equal the hypotenuse squared, which in this case is r, I can replace this x squared plus y squared with r squared. So this equals r squared over r squared, which happens to equal 1. And that's how we know that this identity will always be true. Sine squared theta plus cos squared theta always equals 1. And that's the Pythagorean identity. Here's another identity that's always true. Turns out that the tan of any angle is equal to the sine of that angle divided by the cosine of that angle. We can prove this using the same diagram we used before. And in this case, we're going to prove the right-hand side. So we're just going to focus on this sine theta over cos theta right here. Well, sine theta over cos theta, if we use our x, y, and r, sine theta, of course, was y over r. Cos theta was x over r. Remember, just adjacent over hypotenuse. Well, what's one fraction divided by another fraction? We know we can simplify this by flipping the denominator and changing it to a multiply question. So this is the same thing as saying y over r multiplied by r over x. Well, with these two fractions multiplying, we can now reduce or cancel anything we see that's the same in the top and bottom. So this r right here can reduce or cancel with this r right here, and we're left with y over x. Well, y over x happens to be the opposite side over the adjacent side. Well, we can see in this diagram that tan theta will equal the opposite side over the adjacent side, or y over x. So if tan theta equals y over x, then it must also equal sine theta over cos theta. And that proves our second identity, the quotient identity. These next three identities come from what we call the reciprocal ratios. The sine, cosine, and tangent ratios are called the primary trig ratios. But we do have three trig ratios that are called the secondary trig ratios, otherwise known as the reciprocal trig ratios. These are just the trig ratios of the reciprocals of our primary trig ratios. We always recognize sine, or the sine ratio, as being opposite over hypotenuse. Well, if we take the reciprocal of opposite over hypotenuse, or hypotenuse over the opposite side, we get a different ratio that's called the cosecant ratio. So the cosecant ratio, which we short form to CSC theta, equals the hypotenuse side over the opposite side. It's just the reciprocal. And so the reciprocal identity that is associated with this is that the cosecant of any angle theta is just equal to 1 over the sine of that same angle theta. Cosine and tangent also have reciprocal ratios. The reciprocal ratio for cosine is called secant, and we short form that SEC. And of course, the secant of some angle theta, instead of being adjacent over hypotenuse, is the reciprocal hypotenuse over adjacent. And the reciprocal to tangent we call the cotangent, which is simplified to the letters COT. And instead of being opposite over adjacent, it's adjacent over opposite. We do have to be a little bit careful when we remember each of these different terms and which primary trig ratio they're associated with. Tangent and cotangent are easy to remember that they go together. But oftentimes we think that cosecant goes with cosine and secant goes with sine. But in actuality, they are flipped. Cosecant goes with sine, secant goes with cosine. So a way that I like to remember is that for every pair of a primary trig ratio and a reciprocal trig ratio, there can only be one word that starts with the word co. Tangent goes with cotangent, secant goes with cosine, and sine goes with cosecant. Okay, so now we know the two basic identities and now these three reciprocal identities. So let's put them into action and we're going to try to prove some trig identities. Here's our first one. Prove that the cosine of x multiplied by the tangent of x, all divided by the sine of x, equals 1. You'll see some questions use theta, some other questions use x or some other letter. It doesn't matter. As long as the angle is consistent, we can use our trig identities. For all of these proofs of trig identities, we need to make sure that we follow the proper form. Form matters in this case because we can't make the assumption that this cosine times tangent times or divided by sine will equal 1. We're trying to prove that that's true. So I can't just follow downwards and keep putting equal signs. I need to do a left side, right side formal check. And that will always be true for trig identities. Always do a left side, right side formal check. So let's set up our page where we have a left side and we have a right side. In this case, our left side equals cosine x multiplied to tan x divided by sine x. And our right side just happens to equal 1. Our goal is we want to work our left side so that we can eventually make it equal to 1, which will prove that it equals the right side. And to help us remember that we can't cross over the left side to the right side when doing our proof, I'm just going to put a line here. We can't do anything on the left side that will affect the right side, which means I can't just multiply both sides by sine x to get rid of the sine x over here. We can't move anything across this line. What we can do, though, is use our primary trig ratios. I'm going to write them off to the side here again. Okay, here were our two primary trig ratios. The Pythagorean identity, which said that sine squared any angle, in this case x, plus cos squared of any angle we'll call x, equals 1, and that the tan of any angle equals the sine of that angle over the cosine of that angle. Okay, so for our identity we're trying to prove, because our goal is to get this equal to 1, we're going to need to use our two basic identities inside our own proof. The first rule of thumb here is if we see any tans in our identity, we want to convert them into sines and cosines. And we can do that by this quotient identity, because we know that tan x equals sine x over cos x. So where I see the tan x in my left side here, I can say that equals sine x over cos x. So I'm going to replace that. So I'm going to write cos x because it's already there. I'm going to multiply this by tan x, which is the same as saying sine x over cos x. And then all of this goes over sine x. Now, for anybody that just looks at this, they're going to wonder, how did you replace tan x with this sine x over cos x? That doesn't really make any sense. So when we do our proof, if we use one of our identities, we need to write beside it what identity we used. So in order to go from tan x to sine x over cos x, we use the quotient identity. So I'm going to put a little qi off to the side on the same line that I made the switch. Well, let's see how that helps us. Cosine of x multiplied by sine x over cosine of x. when these things multiply, this cos x is sort of like it's in a numerator. So it can actually cancel or reduce with this cos x that's in the denominator of this fraction. Those things cancel right out. And so what we're left with is this sine x left over here. And we're left with the sine x that was in the denominator here. And sine x divided by sine x, well, that's one thing divided by itself, so that equals 1. And look at that. That's what the right side equals. Funny how that works out. So we end our proof by saying, well, therefore, the left side equals the right side. So our proof is made, and we put a check mark on our identity. Okay, so we're getting the hang of it. Let's try another one. We want to prove that tan squared theta plus 1 equals secant squared theta. Remember, secant squared theta is one of our reciprocal identities. Secant pairs with cosine. So secant is equal to 1 over cosine. To do our proof, we start by writing out a left side and a right side. So the left side is tan squared theta plus 1. Our right side is equal to secant squared theta. We're going to want to change this secant squared theta into its primary trig ratio equivalent. So we're going to use a reciprocal identity here. We know that secant pairs with cosine, so secant squared theta will be the same as saying 1 over cosine squared theta. And we use the reciprocal identities to do that. Let's leave this right side the way that it is for now, and we're going to try to work the left side. Maybe we can get the left side to equal what this right side equals. That's our goal anyway. A rule we used before was that anywhere we saw tan, we want to convert it to sines and cosines, and we can do that with our quotient identity. So tan squared theta is the same as saying sine x over cos x, or sine theta over cos theta, all squared. And then plus 1. Now sine theta over cos theta all squared is the same as saying sine squared theta over cos squared theta. And in fact, from now on, it's permissible for you to go from tan squared theta all the way to sine squared theta over cos squared theta. Even though it's not the exact identity that we see here, it's okay for you to make that leap. But that's the only leap that is allowed. Okay, one thing that I notice is the left side has two chunks of things. It has this sine squared over cos squared, and it has this plus 1. The right side only has one chunk of things, or just one fraction, 1 over cos squared theta. In order for the left side to equal the right side, I'm going to need both sides to have the same number of chunks of things. So let's try to get that left side so that it only has one thing. Or let's combine that fraction with that 1. How do we do that? Well, we do it by doing any other way in which we want to add fractions together, and that's by finding a common denominator. Our common denominator here is going to be cos squared theta. So let's rewrite this 1 so that it has a denominator of cos squared theta. So this is going to be sine squared theta over cos squared theta. That hasn't changed. And now this 1 I'm going to rewrite as cos squared theta over cos squared theta. See how it maintains the value of 1. Well, now that we have a common denominator, we can write our common denominator, cos squared theta, and our numerator now is sine squared theta plus cos squared theta. That looks pretty complicated. So we do a quick little check with the left side and right side. Both sides have the same denominator, cos squared theta, so that's good. The right side has a numerator of 1, So how do we make the left side have a numerator of 1? Well, it turns out one of our other identities is exactly that. Sine squared of any angle plus cos squared of that same angle equals 1. It's the Pythagorean identity. And it's what we have in the numerator here. Sine squared theta plus cos squared theta. So we can say that that numerator will equal 1 based on the Pythagorean identity. So 1 over cos squared theta. And we were able to get that because of the Pythagorean identity. And I just noticed that up here we forgot to say that we used the quotient identity when we converted that tan into sine over cos. And there we have it. The left side, 1 over cos squared theta. The right side, 1 over cos squared theta. Therefore, we've proved that the left side equals the right side, and our identity has been proven. That's the essence of how trig identities work. We take our two simple trig identities and we insert them into bigger trig identities in order to prove that the left side equals the right side. I'm going to go through 2 more examples, but if you'd like to pause the video now or stop it and work on some identities on your own, that would be recommended. And then come back to the video when you want to see a couple of more complicated examples proven. The only way to get good at solving trig identities is to do them yourself. So make sure you put in some time and effort into proving them. And you will get stuck. It's important that you push through and don't give up. And don't look at the answer right away. Try something, and if it doesn't work, try something different. This is really going to test your ability to persevere and to push through, and not just go right to the answer. Okay, we're going to try a couple of more difficult examples. So I want you to pause the video right now and try this on your own first, and then hit play and see if you did it right. Or if you've worked on it for a little bit and you got really stuck, then hit play, watch for a little bit, and then once you get unstuck, try the rest yourself. We want to prove that 2 minus 2 times the sine squared x all over cos x equals 2 times cos x. Let's set up our problem. Left side equals 2 subtract 2 sine squared x all over cos x. And the right side equals 2 times the cosine of x. I like to put these things far apart from each other so I never think to cross them over. The right side right now, 2 times the cosine of x, there's nothing that we can really do. None of our trig identities use just 2 or cosine of x. So we're going to spend most of our time here on the left side. But even on the left side, we're kind of stuck. We don't have our Pythagorean identity, sine squared plus cos squared equals 1, and I don't have any tans, so I can't convert them to sines over coses. So what do we even do? Well, one thing we can do is actually look at the trig identities a little bit closer. And I'm going to look at the Pythagorean identity. Sine squared x plus cos squared x equals 1. Turns out if we rearranged this identity so that we isolate it for sine squared x, look what we get. Sine squared x equals 1 subtract cos squared x when I move it on to the other side. This is still considered the Pythagorean identity, just rearranged. So I'm going to take this left side, and where I see the sine squared x, I'm going to replace it with this rearranged Pythagorean identity. So this equals 2 subtract 2 times 1 minus the cos squared x all over cos x. A big reason why I really like to do that is because if you notice on the right side, I only have cosines. I don't even have tangents or sines. So if I can make everything on the left side all cosine stuff, then eventually I can try to reduce down to what I need on the right side. Don't get tricked here as well into just doing 2 subtract 2. Remember, we need to follow BEDMAS, so this 2 will need to multiply into this bracket first. So let's do that. We'll distribute. 2 subtract 2 times 1 is 2. And then negative 2 times negative cosine is positive 2 cos squared x, all over cos x. And maybe you can see where this is going. 2 subtract 2 is 0. Now those cancel out. And what we're left with is 2 times cos squared x all over cos x. Now we have some powers of the same base. We have a cos squared x and we have just a cos x. This is like saying we have two cos x's multiplied together, divided by 1 cos x. So these 2 and this 1 can reduce. 1 will cancel with one of the others up here, so this squared part. And we're left with 2 multiplied by cos x, which happens to be the right side. So therefore, the left side equals the right side, and our identity has been proven. Rearranging the identities so that you have one that works, and of course we need to remember to put here that we use the Pythagorean identity, can get you out of a jam if you get stuck. So try that next time you get stuck on a question. Alright, here's the last one we're going to try, and it looks kind of daunting. 1 over 1 minus sine x subtract 1 over 1 plus sine x somehow equals 2 tan x over cos x, and we need to prove this. As always, let's set up left side and right side. Okay. A big thing that I noticed right away is that the left side has two different chunks of things. It has two fractions separated by a minus sign, and the right side only has one. So I'm going to try to combine those two fractions by subtracting them, and we'll see where we get. The right side also has a tan x, and we said that a rule is anytime we see tan, we want to convert it into sine over cosine. So let's start with that, and then we'll try to work those two fractions and how we can combine them into one. Tan can convert into sine over cos, or sine x over cos x, all over cos x. And this is by using the quotient identity. Now, 2 times sine x over cos x, all divided by cos x, can simplify like this. 2 times sine x over cos x, that's the numerator, will multiply with the denominator when it's flipped, right? Flip and multiply. So cos x, remember, is the same as just saying cos x over 1. So when flipped, or when taken in a reciprocal, that's 1 over cos x. And when multiplied now, we multiply the numerators and multiply the denominators. So 2 sine x times 1, which is 2 sine x, over cos x times cos x, which is just cosine squared x. We could keep going on the right side by changing the cos x to 1 minus sine squared x. But let's just look at the left side and see what happens, and then maybe we can adjust if we need to. In order to make two fractions into one fraction, we need to subtract. And in order to subtract, we need common denominators. Our denominators might look similar, 1 subtract sine x and 1 plus sine x, but in fact they are not common. And when we did our simplifying rational expressions, we knew that to subtract fractions with different denominators, we needed a common denominator that had both denominators as factors. So our common denominator is going to be 1 minus sine x as one factor, and 1 plus sine x as the other factor. Well, our first fraction only had this 1 minus sine x, so we need to multiply the numerator by the new factor, which is 1 plus sine x. So 1 multiplied by 1 plus sine x is just 1 plus sine x. Same thing goes with this other numerator of 1. So subtract 1 times 1 minus sine x. And I'm being very careful to put this into brackets because of the subtract sign. We're going to subtract the 1 and the negative sine x. Simplifying the numerator, we're going to get 1 minus 1. Those will disappear. And sine x subtract negative sine x, or add sine x. So that's 2 total sine x's. Look familiar on the right side? The numerator now we need to FOIL. So 1 minus sine x times 1 plus sine x is just 1 minus sine x, plus sine x, then minus sine x, and then minus sine x squared, or sine squared x. And if we eliminate those middle terms because they cancel out, we get 2 sine x over 1 subtract sine squared x. So let's evaluate our left side and right side here. It looks like the numerators are the same. The denominators aren't, but you may recognize that 1 subtract sine squared x is actually the same as cos squared x because of the Pythagorean identity. We can make that rearrangement. So I'm going to rewrite this as 2 sine x over cos squared x because of the Pythagorean identity. And with that identity, we've proven that the left side equals the right side and that this identity works. So we just went through 4 different trig identities. And there are tons more with some little tricks here or there to try to solve them. Good luck when you solve yours. And at the end of the day, don't forget that you have the 2 simple identities. Use those to your advantage and maybe rearrange them. And eventually you'll come to the right answer. But mostly, do not give up. Keep trying, and it's okay to get it wrong the first time, and it's okay to get it wrong a second time, and keep trying.